Well, switch to English. He will give a talk about Toeplitz operator and flag manifolds. Please, Matthew.
Thank you so much. I am very, very happy to be able to give this talk. Thank you so much for the invitation. Sorry to take me a second to switch my brain back to English. But yes, as Nikolai said, this is going to be the second talk out of two. Jessica gave the first talk, so this is a joint work with her. And we have worked on Toeplitz operators associated to Bergman spaces on flag manifolds. Okay, yeah. So just a quick reminder, we're looking at Toeplitz operators from the point of view of representation theory here. But really everything in mathematics is connected. There's this nice quote of David Vaughan that says that the orbit method in representation theory is a very nice example of circular reasoning. That you think of representation theory as something that allows you to understand geometry by studying spaces of functions on homogeneous spaces. But I'm sorry?
No. Enrique, your microphone is working. Maybe better you will turn it off.
No oigo.
Yes, Matthew, go ahead.
Yes. Okay. So at the same time, the orbit method, which allows you to assign representations to coadjuvant orbits that are orbits of the coadjuvant action of a group on the dual of its Lie algebra, which is a symplectic manifold. So it's a bridge between symplectic geometry and representation theory. So in other words, the two worlds, each one sometimes helps you with the other, and sometimes one is harder than the other. And it's the same thing with Toeplitz operators, which I think are interesting because they're an example of quantization. And as we all know, in quantum mechanics, geometry through symplectic geometry and representation theory are both pillars of understanding quantum mechanics, and sometimes one helps you more than the other. So we'll be taking a look at Toeplitz operators on these flag manifolds from the point of view of representation theory. So just a very quick reminder for those who might not have seen the Jessica's talk. If you let G be a group, a unitary representation of that group is just an action of that group in a Hilbert space by unitary operators. Okay, so it's just a homomorphism from the group to the unitary group of a Hilbert space. And here, one of the most important concepts is that of an invariant subspace. So it's any subspace where when you act with using the group on vectors in that subspace, you stay within the subspace. And if it's a closed subspace, then that allows you to restrict the representation down to that closed subspace, and you get what's called a subrepresentation.
Invariant subspace means that the image PG or V
belongs
to V.
Exactly. That's a typo. That should be that it's contained in V. Exactly.
Yeah.
Thank you so much. So as usual, if you have that the only invariant subspaces are all of H and the trivial subspace, then we say it's an irreducible representation. And of course, if we have a topological group that's acting, you want things to be continuous. And here, the correct topology to put on the unitary group of the Hilbert space is the strong operator topology. You do not want to put the norm topology on that. Okay, as I said, invariant subspaces are important because they allow you to define new representations. You take any invariant subspace V and you restrict the action of the group down to that subspace, and it gives you a new representation of the group on that subspace called a subrepresentation. And another thing you can do with representations is if you have two of them, you can define a direct sum. So you just now act on the direct sum of those two Hilbert spaces. Sorry, this is another typo. This should be pi direct sum rho here. Acts by pi on the first factor and rho on the second factor, right? Okay, so one of the first things you learn about unitary representations is that they always decompose as a direct sum of subrepresentation. So if you have that V is an invariant subspace, then its orthogonal complement is also invariant. And so you decompose the representation on H as a direct sum of the subrepresentations on V and V perp. So in particular, sorry, this is another error. This should be finite dimensional unitary representation. If you have a finite dimensional unitary representation, then it decomposes as a direct sum of irreducibles. This is not true in general if it's an infinite dimensional
it might be direct integral in general.
Yes, it might be a direct integral instead of a direct sum, but it will always be a direct integral of irreducibles. But I meant to say finite dimensional here. Okay, and as usual, when you define a mathematical object, you need to know what the morphisms are. And here, the morphisms are what are called intertwining operators. So if you have two representations here, pi and rho, then a morphism or intertwining map from pi to rho is it's going to be a bounded linear map from the Hilbert space H to the Hilbert space K, and it needs to literally intertwine the representation. So T applied to pi of G has to be rho of G applied to T. Okay, so it's just transferring the action from one space to the other. Was there a question?
What was?
So I was asking if there was a question. I thought I heard someone.
No,
say
no.
something.
So far,
Okay.
no.
So two representations are equivalent if you have an invertible intertwining operator between them. Okay, and we have a notation for the space of all intertwining operators. In fact, if you just grab one representation, you consider the intertwining operators from that representation to itself, what you get is a von Neumann algebra. Okay, because it's an algebra, it's a star algebra, and it's closed under the weak operator topology.
Mhm.
I'm assuming that these are unitary representations still. Okay, so as you can see, the irreducible representations are key to all of this. If you, for instance, are interested in finite dimensional unitary representations, it's enough to just understand what the irreducibles are, and then you know what all the finite dimensional representations are up to equivalence. They're just sums of irreducible ones. So we'll denote by G hat the set of equivalence classes of unitary representations of a group. And the first part of the famous Peter Weil theory for compact groups says that if you have a compact topological group, then every unitary representation decomposes as a direct sum of irreducible representations, which are all finite dimensional. Okay, so in this case, it is true that it decomposes as a direct sum of irreducibles, and in fact, you can talk about the multiplicity of a representation. So I've chosen here one representative for each equivalence class of irreducible unitary representations, and if you take any unitary representation, there are going to be unique multiplicities associated to every equivalence class of representations, so that this big representation, sorry, another typo, this should be sigma, is just equivalent to a direct sum of m lambda pi lambda, where m lambda pi lambda is a representation that's just a sum of m lambda copies of pi lambda. Okay, so these are literally the multiplicities. I skipped ahead quite a few there. Okay. Okay, so like I said, the moral here is that for a compact group, the key is to understand how to construct and classify all the irreducible unitary representations. And in this talk, we'll be focusing almost exclusively on the compact group U of n, although basically all the results we have for Toeplitz operators at the end work for any compact group, any compact, I should say, any connected compact Lie group. So the unitary group, as usual, is just the group that consists of all unitary matrices. And there's a sense in which it can be complexified, and the complexification of this group is just the group of all invertible n by n complex matrices. Both of these are examples of linear Lie groups. That is, they're closed subgroups of GLNC for some n. And one of the keys to understanding linear Lie groups is their Lie algebras, which are easy to calculate. So the Lie algebra of GLNC is, you can just define it to be the space of all n by n matrices, but algebra. So it needs a Lie algebra structure, and that's just the commutant of matrices. This should be GLNC. Now, if I take some closed subgroup of GLNC, then its Lie algebra is going to be given by the subspace of all matrices X, such that the exponential of T times X is in the group for every T real. Okay. And you can prove basically using linear algebra and first order differential equations that this G here is in fact a Lie subalgebra of GLNC. So if I take, first of all, it's a vector subspace, and if I take a Lie bracket of two things in G, I'll stay in there. Okay, and in this case, the Lie algebra of the unitary group consists of precisely the anti-Hermitian matrices. So one thing I want to point out is that classifying the irreducible representations of the group U of n is the same thing as classifying, is almost the same thing, I should say, as classifying the irreducible representations of its Lie algebra U of n. Okay, it's almost the same thing because it turns out there are more representations of its Lie algebra than of the group U of n, because U of n is not simply connected. Okay, so how does that work? You take two linear Lie groups, G and H, with their respective Lie algebras, and let's suppose you have a continuous group homomorphism. Well, then you can take its derived homomorphism, which is just to take the derivative at the identity. So you take some element of the Lie algebra of G, okay, and the derived homomorphism evaluated in X is just a directional derivative, and you define moving in the direction X as taking the exponential of T times X. Okay, so you evaluate rho in X times X in the exponential of Tx, and you take the derivative at T equals 0. This gives you a Lie algebra homomorphism. So it sends Lie brackets to Lie brackets, it's linear, and it satisfies that rho of the exponential of X is the exponential of d rho of X. And one of the first theorems you learn about linear Lie groups is that this exponential map from a Lie algebra to its Lie group is a local diffeomorphism. So that means that if I have that G and H are, if I have that G as a connected Lie group, and I have two homomorphisms from G to H, and their derived representations are the same, then rho has to be the same, and rho 1 and rho 2 have to be the same for every exponential of X. And that means that they have to be the same homomorphism of all of G, because every open neighborhood of the identity generates a connected Lie group. Okay. So you can do the same thing if you have a finite dimensional representation. If I have a finite dimensional representation, I just have a homomorphism between the group and this unitary group of H, which is a linear Lie group. So we can define its derived representation, right? Just it's the derived homomorphism. And now it goes from the Lie algebra of G to the Lie algebra of the unitary group. And basically using the argument I just very briefly sketched out, you can show that if you have a connected Lie group and you have two representations, these aren't necessarily unitary representations. So that means they're homomorphisms to the general linear group of the vector spaces H and V. Okay, then the intertwining operators between pi and rho are the same, exactly the same operators as the intertwining operators between their derived representations, which means they're equivalent if and only if the derived representations are equivalent. But it's actually much stronger than that, saying that the intertwining operators are literally the same set. Okay, and in particular, a subspace of H is going to be pi invariant, so it's going to be invariant under the action of the group G, if and only if it's invariant under the action of its Lie algebra. Okay, so this is almost saying that studying the finite dimensional representations of the Lie algebra is the same as studying the finite dimensional representations of the group G. And in fact, if the group is in addition simply connected, then every finite dimensional representation of the group of the Lie algebra is the derivative of a representation of the group. And in that case, what you have is an isomorphism of categories between the category of finite dimensional representations of the group and its Lie algebra. But we can go a little bit further, because here we know that U of n consists of the anti-Hermitian n by n matrices. So you can write the Lie algebra of GLNC as the direct sum of matrices that are anti-Hermitian plus I times anti-Hermitian matrices, and I times an anti-Hermitian matrix is a Hermitian matrix. Every matrix can be written uniquely as the sum of a Hermitian and an anti-Hermitian matrix. What this means is that GLNC is the complexification of the Lie algebra of UN. GLNC is a real Lie algebra, but it's also a complex Lie algebra. And as a real Lie algebra, it's the same as U of n plus I U of n. So in fact, it's what we call the complexification of the Lie algebra U of n. There's a way to define the complexification of all real Lie algebras, and it's a functor. It acts just like you would expect. You just extend everything by complex linearity. So if you have some real Lie algebra G, its complexification is just going to be G direct sum with IG as a real Lie algebra.
Matthew, what is the reason for you to consider this complexification?
The reason is the following, that real finite dimensional representations of U of n are the same thing as, finite dimensional representations of UN that are going to be representations of a real Lie algebra are the same thing as complex linear finite dimensional representations of GLNC. And why does that help me? It's because basically GLNC, because it's a complex Lie algebra, is certain things are going to be diagonalizable here that aren't here. Mm-hmm. So if we were to get into root space decompositions, those exist here, but they don't exist here because this is just a real Lie algebra. But because this is a complex semi-simple Lie algebra, the problem is that if you take a maximal torus in U of n, the maximal torus, when asked by the adjunct representation on U of n, has purely imaginary eigenvalues. I'm sorry, purely imaginary eigenvalues, which means that you're not going to find an eigenvalue decomposition of U of n with respect to that action, but you will here. So GLNC decomposes as a direct sum of subspaces when you consider the action of the Cartan subalgebra by the adjoint action. So that's why it's important to pass to the complexification. But at any rate, you're studying the same thing, because every real linear representation of U of n extends magically and immediately, uniquely, to a complex linear representation of GLNC. In fact, you have an isomorphism of categories. It's the same thing, right? So if you have a finite dimensional representation of a Lie algebra G, you can complexify it in the obvious way. So this should be GC here. This should be a representation of GC. And so everything in GC is now a x plus IY, where x and y are in G. So G direct sum IG. So what should pi c of x plus IY be? Well, it needs to be complex linear. It has to be, because I said that's what I want it to be. So it will have to be the same thing as pi c of x plus I pi c of y. But I also want pi c to be an extension of pi whenever I apply it to things in G. So this is the only way to make it make sense. And in fact, this is a functor, going from real linear representations of G to complex linear representations of GC. So in fact, it's an isomorphism from the category of finite dimensional real linear representations of G to the complex linear finite dimensional representations of the Lie algebra of GC. So it's a one-to-one correspondence between representations of G and GC, but the complex linear representations of GC and the real linear representations of G, and it preserves intertwining operators, it preserves invariant subspaces, everything acts exactly the same. And there's one more structure associated to the group that I want to add, and that is the complexification of this Lie group G. Okay, so I need to say briefly what a complex Lie group is. If you have a Lie group with a Lie algebra G, and it happens to admit the structure of a complex Lie algebra, so there's a complex structure, so some map J such that its square is -1, and it commutes with the Lie bracket, so that with respect to that complex structure, you have a complex Lie algebra. Then G turns out to have a unique structure of a holomorphic manifold in such a way that the group product and the inversion on the group are holomorphic. And so it's a complex Lie group. And it's such that if I consider a group homomorphism between complex Lie groups, it's going to be holomorphic precisely when the derivative is complex linear. The derivative is always a homomorphism of real Lie algebras whenever it's a continuous homomorphism. But if in addition it's C linear, then it's a homomorphism of complex Lie algebras. Okay, So why do I say that? Because I end up with this final chart of all the different structures that are basically the same thing. I have finite dimensional representations of the group UN. I have finite dimensional representations of the same thing as studying complex linear finite dimensional representations of GLNC. And if I have a holomorphic finite dimensional representation of GLNC, its derivative is a complex linear finite dimensional representation of its Lie algebra. And in fact, even though this arrow and this arrow only point one direction, it turns out that following this chain, I actually get an isomorphism of categories between these two representations. Every finite dimensional representation of U of n can be extended by analytic continuation uniquely to a holomorphic finite dimensional representation of GLNC. So again, I'm looking at the same problem from several different angles. So this is important because right now I'm going to give, without proof, I'm going to talk about what the classification of the irreducible representations of U of n looks like. And to do that, I first need to take a detour into flag manifolds. So a flag, and these are called flags because if you imagine like drawing a picture of a flag, you start by drawing a point and then you draw a line, right, for the flag pole, and then you draw a square, which is two-dimensional for the flag itself, right? So that's not a perfect analogy, but that's why they're called flags. A flag in say Cn, which is this finite dimensional vector space, it's just a chain of, it's an increasing chain of vector subspaces of Cn, and it has to start with the trivial subspace and end with all of Cn. Okay, and I'll say it's of shape n1, n2 up to nk, where these are strictly positive integers, and each one is strictly less than the next one. If the dimension of each of these intermediate vector subspaces is exactly equal to n1k, respectively. Okay, so I'm fixing the dimensions that I want these subspaces to have, and then I just consider it an increasing chain of subspaces of those dimensions. A full flag is what it's called if I have a chain where I have a subspace for every possible dimension, right? So that would mean that I have the trivial subspace, which is just the point, the subspace containing the point 0. I'll have a one-dimensional subspace, and then a two-dimensional subspace that includes the one-dimensional subspace, and then a three-dimensional subspace. And I have everything all the way up to, and then the minus one-dimensional subspace, and then the whole thing. Okay, so that's what a full flag is.
Matthew, one question, please.
Now,
Matthew, one question. There is equivalent alternative way, just decompose Cn in the orthogonal sum of.
so I think you can hear me, but I can't hear you.
What is the advantage to consider flag compared with orthogonal decomposition?
Let me see.
Maybe I don't hear you.
I think Matthew is not hearing us.
Matthew.
Okay, I can hear you now.
Yeah, now yes. So what is the advantage to consider flag compared with orthogonal sum decomposition of neighbors? Orthogonal complements of neighbors of flag elements. Matthew, your mic is off.
Okay, it won't let me unmute myself on the other one that I'm joined in.
Okay. So go ahead.
It says, but it's not letting me, and I hear a big echo because it's not letting me re-unmute my audio on my audio connection.
Mhm.
Could somebody help me with that?
No, we hear you perfectly.
Yes, but the problem is I now hear an echo and I can't concentrate because I hear myself in my ears.
Okay.
So I just need somebody to let me unmute myself here. Well, if not, I can try to continue.
Yeah.
Matthew,
Hmm?
just activate your microphone in your phone.
I can't. It says el anfitrión no permite que los participantes reactiven su micrófono ellos mismos.
Anyway, go ahead, Matthew.
I'll try, but it's very difficult because I hear an echo of myself like a second later. Okay, this is very difficult. So so we have, okay, I'm sorry, I'm gonna have to, okay, I'll try to continue. I just need to unmute myself here and it won't let me.
We are not hearing you.
Yeah, okay, this is very difficult because I hear myself. I'll try to tune myself out. Okay, I took one out, headphone out. Okay, so so I was saying that you have it's very difficult to talk when you hear yourself on an echo 1 second later. So you have an action of the group GL in, I'm sorry, I won't be able to hear anyone, but I'm gonna have to take this headphone out. I'll keep talking, but I just can't talk hearing this. So if anybody wants to ask me a question, please write it in the chat.
Mhm.
Okay, so now I can keep talking. So we have an action then of the group GLNC on the flag manifold. And this just acts individually on all the subspaces that make up the chain of subspaces in the flag. Okay. So you just pick an element of GLNC, and now you'll just act individually on each subspace from V1 to VK using the group. So you just consider the range of G applied to that subspace, and that gives you a group action. Okay. Creo que el problema es que soy coanfitrión con este cuento o algo, porque luego me dice que el anfitrión quiere que hables, pero cuando intento reactivar mi micrófono, dice que el anfitrión no permite que los participantes reactiven su micrófono ellos mismos. Perdón, ok. Entonces, voy a denotar por, I'm going to denote, sorry, by Fn, the space of all flags of a particular shape N1 through Nk. And now I'm going to write F full for the space of full flags. So these are flags which have subspaces of every dimension. Okay, I'm going to choose a particular base point flag, and for a certain reason, I'm going to do it by letting W sub I be the space of all elements of Cn that are allowed to be non-zero in the rightmost I in entries. Okay, so this is the opposite of the standard condition, but that's because I'm going to be using the opposite rail group in a moment. Okay, so it turns out that the unitary group U of N and therefore the bigger group GLNC act transitively on all of these flag spaces. It's like these are called flag varieties or flag manifolds because these are in fact homogeneous spaces and therefore they're the same as quotients of GLNC or U of N by certain subgroups. Okay, they're also algebraic varieties. And that allows you to, because they're just sort of quotient spaces of GLNC and U of N, that allows you to transfer smooth manifold structure to them. To see what I mean by this, so let's choose an element of U of N, and I'm going to suppose that G fixes the base point for the full flag manifold. Okay, so here the base point is such that W1 here is just the subspace that's one-dimensional, and you're only allowed to have things distinct from 0 in the last entry. Okay. Now, if G fixes this subspace W1, then it has to fix both W1 and its orthogonal complement because it's a unitary operator, which means that it has to act unitarily on each one. So it has to act by a complex number of modulus 1 in this lower corner, and then it has to have a unitary operator on Cn minus 1 up here in this corner. Okay, so then continuing on, we see that G has to be diagonal.
Mm-hmm.
The echo is getting worse. Now I'm 3 or 4 seconds out of phase. No hay forma de que me puedan ayudar a desactivar, a activar el micrófono aquí.
Oscar, ¿puedes hacer algo al respecto?
I'm sorry?
Ya quité su otra sesión. Matthew, ¿puedes hablar?
Ok, ahora dice que fui eliminado acá y ahora no voy a poder escuchar a nadie porque solo puedo escuchar con mi celular. Pero puedo seguir hablando. Pero no voy a escuchar a nadie porque no funciona el audio de mi compu, solo el micrófono. Pero puedo seguir hablando. Solo voy a necesitar que me permitan reentrar con mi celular.
¿Puedes entrar, por favor?
Sí, no me deja entrar. Dice, usted no puede volver a unirse a esta reunión porque fue eliminado previamente por un anfitrión. Pero sigo hablando, entonces. Si alguien me puede ayudar a entrar, sería excelente.
Sí, ahorita lo vemos.
Voy a tratar de hacerlo. No, todavía no, porque fui eliminado por el anfitrión. O a lo mejor si llamo el número, a lo mejor hay un número telefónico. Bueno, pero ¿alguien puede escribir un chat si me siguen escuchando?
Sí, sí, te escuchamos.
Nicolai, ¿me das una señal si me escuchas? Ok, perfecto. Perfecto. Entonces sigo hablando. Tenemos entonces que we have then that the that if I have some element of U of N that fixes this base point, then it will have to be a diagonal matrix. And because it's a diagonal matrix in U of N, it has to be diagonal with entries in S1. So the full flag manifold is just the quotient of this unitary group by this maximal torus T. So now I'm going to suppose that I have something in the bigger group, GLNC. and that it fixes this same base point. It turns out that then G has to be a lower triangular matrix, and that the entries on the diagonal had to be distinct from 0. So this is one reason to consider these increasing flags instead of just the orthogonal subspaces that Nikolai was talking about, because here this group does not decompose as block diagonal matrices. You can see how GLNC actually fixes the one-dimensional space, the two-dimensional space. I'm sorry, this group B bar fixes the one-dimensional space, the two-dimensional space, the three-dimensional space, the four-dimensional space, etc. But this group does not fix the, it does not leave invariant the orthogonal complements. Because here I'm considering the action of a group that's not the unitary group, but just the full general linear group. Okay. This is called a Borel subgroup of GLNC because it's a maximal solvable subgroup, and it's the opposite Borel subgroup to this one, which has upper triangular matrices with non-zero elements on the diagonal. So it turns out that every Borel subgroup in G is conjugate to both of these. In fact, these two groups are conjugate to each other. They're conjugate to each other if you conjugate by the anti-diagonal matrix, which has all ones on the anti-diagonal. And in fact, the intersection of the unitary group with either one of these groups is just T. It's just the group of diagonal matrices with complex numbers of modulus 1 on the diagonal. Okay. So we therefore have that the full flag manifold is in the quotient of this bigger group, GLNC, by the subgroup that fixes the base point, B bar. As and this is an equivalence of spaces that have an action of GLNC. So therefore, there's going to be a diffeomorphism from UN mod T to GLNC mod B bar, and this can be given by just writing this coset GT and sending it to the coset G B bar, and this map is equivariant with respect to the action of U of n. In fact, it's not too difficult to see why this has to be a complex manifold. We would need to get into a little bit about the structure of GLNC, but it's easier to see why this is a complex manifold, and therefore you transfer that complex structure over to U of n mod T. One way of seeing it is that, in fact, the space of strictly upper triangular matrices can be embedded as an open dense subset of the flag manifold. And these are allowed to have any complex entries. So this is a compact holomorphic manifold. Okay, and in fact, not only that, but it's a holomorphic action manifold on which GLNC acts holomorphically. So this map from this cross product, from this direct product to the quotient space is holomorphic, and in particular, both U of n and GLNC act by biholomorphisms on the flag manifold. But so it's a compact manifold, so the only holomorphic functions turn out to be constant functions. But we can construct certain line bundles over this full flag variety, which have non-trivial but still finite dimensional spaces of holomorphic sections. And these spaces of holomorphic sections on line bundles give you every example of an irreducible representation of U of n. So how do we do that? So first, I just want to briefly mention the other flag manifolds and of other shapes. So I fixed a shape N1, N2 up to Nk, and I fixed this base point where I'm increasing the dimension of the space, but these are all subspaces where you have a certain number of zeros on the left-hand side of, and you're only allowing the rightmost N1 up to Nk entries of Cn to be distinct from 0. So if you have a unitary operator that fixes this flag base point, then what you get is a block diagonal unitary matrix, where each block is a unitary matrix in, sorry, this should be U of ni minus u of ni minus 1.
Mhm.
So it's the dimension of the orthogonal complement of
two neighbors.
n1 inside wn1 inside wn2, which is n2 minus n1. So you'll have u of ni minus 1 here. So you have block diagonal unitary matrices. So this group is a direct product of u of n's. And if you look at the elements of GLNC that fix this base point, you get something that's block lower triangular. So all of these diagonal blocks, and here I put the correct dimensions, ni minus 1s, have to be invertible, but you're allowed to have on the rest of the lower triangular portion of this group, you're allowed to have any complex entries. This is what's called a parabolic subgroup, and that's because it's a group that contains a Borel subgroup. Every group between a Borel subgroup and the full group is called a parabolic subgroup. And this is the opposite of the parabolic subgroup Pn, where they're upper block triangulars. There should be block upper triangular. And again, the intersection of the unitary group with these parabolic subgroups is just this group Ln, these block diagonal unitary matrices. This will still be important in a moment, but again, this manifold is the quotient of GLNC by the parabolic subgroup P and bar, and once again, it turns out to be a holomorphic homogeneous manifold. And you can show that every holomorphic homogeneous space of U of n is one of these. It's equivalent to one of these. These are the only ones. Okay, so how does this help us construct irreducible representations of U of n? So it turns out that these irreducible representations of U of n are in one-to-one correspondence with all tuples in this lattice, where I have n tuples of integers, where lambda 1 through lambda n, where lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda n. So these are decreasing n tuples of integers. And another way of writing this is I can, there's a sort of basis you can write for this lattice. You choose what are called the fundamental weights. Omega I is just the sum, so I'll choose the standard basis for Cn, E1, E2 up to En. So Ei here is just the vector with 1 in the ith entry and zeros everywhere else. Omega I is going to be the sum of the first I of these. So it's the vector that has 1, 1, 1, 1, 1, I times, and then zeros. And then I can write everything in lambda plus uniquely as an integer linear combination of omega 1 through omega n, where omega 1 through omega n minus 1 have to be non-negative integers. Okay, so this is a sort of basis in quotes for this lattice lambda plus. Okay, now each one of these lambdas will allow me to define a one-dimensional representation of these groups B and B bar. And how do I do that? Well, I can just, these are upper and lower triangular matrices. What I can do is I can raise elements on the diagonal to a certain power, a certain integer power. So I can raise a1 to the lambda first power up through an to the lambda nth power. Okay, in fact, this is well defined as a character of the group B. So chi lambda of B1 times B2 is chi lambda of B1 times chi lambda of B2. Right? Because when you multiply two upper triangular matrices, the elements on the diagonal are just the products of the corresponding elements of the diagonal. Okay. Now, what is the highest weight vector? If I take a finite dimensional unitary representation of U of n, and I fix lambda in the lattice lambda plus, a highest weight vector for the representation pi is going to be some vector v in H, such that whenever I act by elements of the group B, I send v to a constant multiple of itself. Now, you may be saying I fixed a representation of U of n, how can I be acting with anything in B? Well, that's because every representation of U of n that is finite dimensional extends uniquely to a holomorphic representation of GLNC. So it makes sense to apply any element of GLNC to a vector in H. Here, I'm saying that this is a highest weight vector if I can apply any upper triangular matrix to V, and I get a multiple of V. And I say that V is of highest weight lambda if pi of V applied to V is actually this character of V times V. Okay, that should be pi of V applied to V. So if I have an irreducible representation of U of n, the highest weight theorem tells me that there's a unique highest weight vector of a unique highest weight lambda in lambda plus. It should be lambda plus. And for each lambda in lambda plus, there's a unique irreducible representation of highest weight. So this is precisely the way of associating an irreducible unitary representation to one of these tuples. Okay. So I briefly need to mention a little bit of Peter-Weil theory. So I'll let G be a compact group, and I'll let L2 of G be the Hilbert space where we use the normalized Haar measure, which is invariant under translations of the group. So we have this left regular representation where the group acts by translation of functions. And this representation is unitary because Haar measure is invariant under translations of the group. Now, if I have a unitary representation of the group, I can define what's called a matrix coefficient function with coefficients V and W, and that's just literally the function that sends G in the group to the inner product of V with pi of GW. So this is literally a matrix coefficient of pi of G for each G in the group. Okay, these are very important in harmonic analysis, and that's because of what's called Schur's orthogonality relations, which tells you every matrix coefficient function of a compact group is of an irreducible representation as an L2 of G. And in fact, if I take two inequivalent irreducible representations of G, then all of their matrix coefficients are orthogonal in L2 of G. And finally, if I take the same representation and two matrix coefficient functions for pi, then what I get is almost the same as the product of V1 and inner product of V2 and the complex conjugate of W1 inner product with W2. But I have to adjust by dividing by the dimension of pi. Okay, so this allows me to take the inner product of any two matrix coefficient functions. And in fact, the Peter-Weil theorem tells me that the matrix functions, if I choose an orthonormal basis for every irreducible representation of G, then that will give me an orthonormal basis for L2 of G, just considering all the matrix coefficient functions with respect to those orthonormal bases. Okay, but I want to make one crucial observation here. So if I take the inner product with a V with pi of x inverse GW, that's the same thing as pi of xv, pi of GW, because pi is unitary. So if I apply L of x to the function pi VW, that's the same thing as pi with coefficients pi of xv and w, which means that I now have an intertwining operator. If I fix w as a normalized vector in H, then this map that sends V to the matrix coefficient function with coefficients V and square root of the dimension times W, that's an isometric intertwining operator, and it embeds pi inside of L2 of G. Okay, that's very important, because now I can tell you how you construct those representations that I talked about. First of all, I'm going to define this space, this twisted space L2 chi lambda of U of n mod t, which is the space of all square integral functions on U of n, such that f of gt is chi lambda of t inverse times f of g for all g and U of n and t. These are precisely the same as the square integrable sections of this line bundle over U of n mod the torus t, which is defined by you take all pairs of elements of U of n and elements of C, and they're equivalent if there's some element of the torus such that so you have x comma z is equivalent to xt and comma chi lambda t inverse z for all elements t of the torus. Okay, and finally, I can tell you how these representations can be constructed analytically. They're also algebraic constructions, but the analytic construction is in the form of holomorphic sections of a line bundle. And for those who study Berkman spaces, this should be very familiar. I started with an L2 space, And now I'm just going to consider holomorphic functions inside it. So the Borel-Veil theorem tells you that the irreducible representation of U of n of highest weight lambda can be identified with this subspace of L2 of U of n. So I consider all the functions that are square integrable sections of U n mod t that are holomorphic sections of this vector bundle. This is a holomorphic vector bundle. I said that U of n mod t is actually a holomorphic manifold, and this is actually a holomorphic vector bundle. Well, one way of saying what the holomorphic sections of that vector bundle are, they can be identified with all the holomorphic functions on the complexification of the group. So this is GLN C to the complex numbers that are holomorphic and that satisfy this equivariance, covariance condition. F of GB needs to be chi lambda B inverse times F of G for all elements of this opposite Borel group B bar. Okay. And finally, if I already have some realization sigma H lambda of the representations of highest weight lambda, I can turn those into holomorphic sections of this line bundle by just considering the matrix coefficient function sigma W comma V lambda, where I choose V lambda to be a normalized highest weight vector. Okay, so this space A lambda, you can see it multiple ways as a space of a particular space of matrix coefficient functions for the representation with highest weight lambda, or a space of holomorphic sections of this line bundle. So we have the Bergman projection, which just is going to project me orthogonally from the L2 space of sections to the space of L2 sections to the space of holomorphic sections. And this is just going to be convolution with this, well, up to multiplication by the dimension of the representation. It's just going to be the convolution of a function phi in this space with this function, this inner product. I'm sorry, this matrix coefficient function sigma v lambda v lambda. So this is the integral over g of phi of y sigma v lambda y inverse x, but sigma v lambda y inverse x is just the inner product of sigma of y v lambda with sigma of x v lambda. So this gives you your Bergman kernel as a function of y and x, and this function sigma v lambda is called a conical function. And it's one of the few matrix coefficient functions which have very nice explicit realizations for U of n. I can tell you explicitly what they are. So first of all, for every I between 1 and n-1, I'm going to define it to be delta I of x to be the determinant of x, over delta n-I tilde of x, where delta n-I tilde, this thing, is the n-I principal minor starting from the lower right corner. So I take the determinant of that n-I by n-I submatrix, and I take the determinant of g, I take the quotient, and that is my delta I of x. And finally, that's for I between 1 and n-1. Finally, delta n is just the determinant of the matrix. So delta lambda, this matrix coefficient function, is just delta 1 of x to the power of lambda 1 times delta 2 of x to the power of lambda 2 all the way up to delta n of x to the power of lambda n, if lambda can be written in terms of the fundamental weights this way. Okay, so we define our Toeplitz operators as always. You multiply and then project. You can show that this operator is sending bounded functions to this should be the space of linear maps from H lambda to H lambda, and this should be the space of linear maps from A lambda to A lambda. This extends to a continuous operator from LP to the space of endomorphisms from A lambda to A lambda. And that Schatten P norm is less than or equal to the dimension always. So in particular, you can extend it all the way up to L1. You can take a Toeplitz operator with an L1 symbol. But this should be end A lambda, and this should be end A lambda. This is a finite dimensional space. The space of linear map from A lambda to A lambda is a finite dimensional space. It's always surjective. And I can tell you what the kernel is and what the orthogonal complement of the kernel is in terms of tensor product representations. So the co-range of this operator T lambda sending a symbol to its Toeplitz operator in L2 is going to be the span of all pi v0, where pi is irreducible and v0 has to be a vector in this space k lambda pi, which is the span of all projections of this vector v lambda tensor v lambda bar to the space of to the kth copy of pi is a sub-representation of this tensor product representation. So this is a bit combinatorically complicated, right? There are formulas for the number of copies of pi in this tensor product representation in terms of lambda, but they're combinatorically complicated. But in theory, this tells you exactly what the corange of this operator T lambda is, and T lambda is always surjective. In fact, it's enough to consider smooth functions. And again, this all comes back to using approximate identities. And finally, you can show that the Toeplitz operators with H invariant symbols are equal to the algebra of Toeplitz operators with H invariant symbols for any subgroup H. And it's equal to just the space of intertwining operators for the representation of G on H lambda restricted down to H. Okay, so that means that Toeplitz operators are going to commute it precisely when the restriction to the subgroup H is multiplicity free. And one example is unitary irreducible representations of UN restricted to UN minus 1 are always multiplicity free restrictions. So these symbols always come. I think this is another example, but I still have to work out some of it. We still have to work out some of the details. The Bayesian transform can also be written out explicitly. This is just what the Bayesian transform always is. And here we have the Bergman kernel is a multiple, the dimension times this conical function, d lambda. So that means the Bayesian transform is going to be convolution with respect to the absolute value squared of this conical function. Okay. The range of b lambda, again, is the space k lambda. And if you restrict b lambda down to k lambda, you get an invertible map that's also a U of n intertwining operator. And in fact, you can say a little bit more than that. You can say exactly what the Bayesian transform of this matrix coefficient function is. And it's going to be another matrix coefficient function of the same irreducible representation pi with the same first coefficient up to this multiple of the dimension of H lambda divided by the dimension of the representation pi. And then the vector on this side gets, you have to apply this other map b lambda pi, which again takes into account the projection of v lambda tensor v lambda bar to the kth copy of pi in the tensor product representation. So I need to take pi to be a nearest representation of appears in this tensor product. So this is a positive G intertwining operator, and it's invertible from k lambda to k lambda. And finally, this allows us to consider the Hilbert-Schmidt inner product of two Toeplitz operators. So the trace of TF times TG star is just the same as this matrix coefficient for the Bayesian transform, b lambda. And so, in fact, this is enough to tell you that the Bayesian transform is just 1 over the dimension times the operator T lambda that sends symbols to Toeplitz operators adjoint faces T lambda. Okay. So I can also tell you that the trace of a Toeplitz operator with symbol F is just d lambda times the integral of F, as you would expect. And the trace of this Bayesian transform is the dimension d lambda. In fact, this isn't so surprising because in some sense, the Bayesian transform should be converging to the identity. And in fact, that's what happens almost. So if you take one of these n tuples, it's a linear combination of fundamental weights, and we're going to consider representations with highest weight lambda and highest weight that's a multiple of lambda for some integer, positive integer m. I'm going to create a shape n1 through nk where I'm only going to pick out the coefficients of lambda with respect to omega 1 through omega n minus 1 that are strictly positive. Okay, so I only want these to be the ones where these coefficients are strictly positive. And I'll consider the corresponding subgroup Ln of U of n, which is a group of block diagonal unitary matrices. Then if I take the limit of the Bayesian transform associated to m times lambda as m goes to infinity, then what I get is the average of f on the right-hand side by L of n. Okay. So this is almost giving me the identity. In fact, if I started out with lambda such that the coefficients from omega 1 to omega n minus 1 are all strictly positive, then this will converge to the identity for functions of U of n mod t, because functions of U of n mod t are already t invariant on the right. And in that case, L of n just turns out to be t. But if you take a more degenerate lambda, then what you get is actually an averaging of f on the right by asymptotically by this other group, L of n. So I'm very sorry that I haven't been able to hear any questions from you all. I'm going to try one more time to enter. Let me see if it lets me. Nope, it still won't let me re-enter on my phone. So I have no way of hearing, unfortunately. Oh, let me pull up the chat. It's also not letting me pull up the chat here. Okay. Okay, what bibliography do you recommend? To read about the Borel-Veil theorem and flag manifolds? Unitary representations of U of n. So there are a couple of representations. If you want a, I'm sorry, there are a couple of groups. I'm sorry, books. I have this weird thing in my brain where the words for book and group got switched over a while back. So there's a book by Goodman and Bullock. So let me see if I can type this into the chat. This is, yes, I'm typing in Goodman and Bullock. It's something like symmetries, invariants, and something. I can't remember what the third thing is. But that book takes a very concrete look at the classical groups. So U of n, SUN, SPN, etc. And it also takes a very algebraic approach and combinatorial approach. It has lots and lots of details. Another book that's nice, that's a nice analytic introduction, and specifically has all the work for U of n without getting into the other compact groups, is a book by Jacques Perrault called Analysis on Lie Groups, an Introduction. One book that has a nice proof of the Borel-Veil theorem is the book by Mark Stefanski on compact Lie groups. And a more I see what the problem was. I was sending direct messages to Departamento de Matemáticas. So let me resend these. Okay. I said Goodman and Bullock. I said Jacques Perrault, Analysis on Lie groups, an Introduction. And I said Mark Stefanski, compact Lie groups. Another excellent book is the one by A.W. Knapp on something representation of semi-simple groups, an overview based on examples. And it has a nice proof of the Borel-Veil theorem, and it states it just the way that I did on which slide was it? Because it defaulted again to only sending a direct message. Okay, that's strange. Okay. Yes. And one more. Okay. I've now restarted my phone, which they asked me to do. So I'm going to see if I can now log in again. It was telling me that I couldn't log in because they had expelled me from the meeting. So we'll see if this works. Okay. Well, thank you very much, Igor. See. Click on this, maybe it will let me in. No, es que no me va a dejar entrar otra vez porque dije que fui eliminado por el anfitrión. Así que me sacaron. Alguien me sacó, el anfitrión me sacó y por eso no me va a dejar entrar otra vez. ¿Sería que en el departamento de matemáticas me pueden dejar entrar otra vez o algo? Yes, I'm very sorry about this chat discussion situation. I'm very sorry for how this turned out. Lo estoy intentando otra vez. Okay. Me dijeron que they said it might be because of the problem that I'm using the same network for my phone and my no, conecté desde otra red y todavía no me deja entrar. Es que alguien me sacó. No sé si a lo mejor fui yo por accidente, pero alguien me eliminó y por eso no me deja entrar otra vez. Pero muchísimas gracias. Una disculpa a todos, perdón por cómo terminó esto.
Okay. So it's very difficult to have a discussion by chat. We thank Matthew again. And Maribel, who's next?
Rosario is next.
Rosario. Rosario and después Armando.
Sí.
Ok. Entonces, gracias a todos y nos vemos próximo miércoles.
Hasta luego.
Gracias, hasta luego.
Hasta luego.